myself onto volume. So let's see. Oops. Okay. So let's see. Okay, let me just swap it a bit around. Okay, one should think that this might work. However, Frank, can you say something?
Sure. I can hear you okay.
Yeah, right. Okay, perfect. Good. So everything is good. All right. With that, we should kick off our session. So it's a pleasure to introduce Frank. So Frank is one of the leading experts in computational approaches to quantum many-body systems and has really pioneered many interesting novelties in that area and used them to understand things like topological phases of matter. So in particular, he has understood the representations of symmetry-protected topological phases in one-dimensional phases in terms of matrix product states. He's worked on the finite entanglement scaling to understand criticality in 1D systems in such numerical simulations. And recently, one of his focus areas has been on the non-equilibrium dynamics of quantum many-body systems, where again, he has pioneered use of these numerical techniques, both in 1D and 2D systems to understand dynamics and excitation spectra. So Frank has completed his PhD in 2006 at the Max Planck Institute for the Physics of Complex Systems in Dresden. He was then a postdoc in Berkeley before moving back to MPI PKS in 2011 as a group leader. And in 2016, he has taken up a professorship at Technical University of Munich. During his career, he has won many prizes, including the 2007 Otto Hahn Medal of the Max Planck Society and the 2015 Walter Schottky Prize. And recently, he has won an ERC Consolidator grant. So today, we're looking forward to an introductory lecture on far from equilibrium dynamics of systems with conservation laws. Over to you, Frank.
Okay, thanks, Gunnar, for the very kind introduction and for the opportunity to present some of our work here and talk at this very nice conference. So as Gunnar announced, I'm going to give a little bit of an overview and some introductory information about far from equilibrium dynamics of systems with conservation laws. And during this presentation, I'm going to discuss work done together with several collaborators, including Tibor Rakowski, who was a PhD student in my group and recently moved to Stanford, Kurt from Kaiserling, from Birmingham, Pablo Sala, who is also a PhD student in my group, Ruben Veriesen, who was a PhD student who recently moved, well, a year ago, moved to Harvard, my colleague Michael Knapp, and part of the work was done together with the group of Monika Eidelsburger performing code atom experiments on some of the ideas I'm going to present. So let me start the talk with a quite general introduction where I want to motivate the problem and phrase some of the questions that I'm going to address. So very broadly speaking, I want to discuss about thermalization, a process that we are very familiar with. So if we prepare a system out of equilibrium and we wait, in particular during a summer day, eventually the inside of the glass will equilibrate with the surrounding, and eventually we'll have a system that will be in thermodynamic equilibrium. So now we can carry over this directly to the world of a closed quantum system, where the entire universe, if you wish, is given by a pure quantum state that we can prepare. And in the experiment, or the thought experiment that I'm conducting now, I'm preparing a simple product state where we have, for example, spin 1/2 degrees of freedom that can be chosen somewhere randomly on the Bloch sphere. So now I'm performing a time evolution. So I just evolving this sort of randomly chosen product state with respect to some generic Hamiltonian. Right? So I'm just assuming that this is now some non-fine-tuned Hamiltonian, and the generic expectation is that during this time evolution, a lot of entanglement will be produced, right? So while initially we might have started with a state where there's no entanglement between the degrees of freedom, we then have a lot of entanglement between the degrees of freedom. So none of them can be really measured individually, and thus we have this kind of blurry color here. Both the initial state is a pure state and also the final state is a pure state, because we are considering the time evolution or the unitary time evolution of a closed quantum system. So globally speaking, certainly nothing has thermalized because we are always at zero entropy. However, we can now play the following game. We can say that instead of globally looking at the system, we are just looking at a subsystem. So for example, we just cut out a block of consecutive spins, and we just look at the reduced density matrix. For this specific initial state chosen, the initial state has a reduced density matrix, which again has entropy 0. So it's still the reduced density matrix of a pure state. However, following the time evolution, there's a lot of entanglement between degrees of freedom inside of this box and outside of this box. So the reduced density matrix is now a density matrix of a highly mixed state. And the conjecture is that the reduced density matrix describing all the degrees of freedom of this block can be actually described by a thermal density matrix that only depends on a few kind of globally conserved quantities, such as the energy that yields a temperature or a particle number that gives you the density, etc. So this is a very generic picture. So, and now one thing that we are interested in is trying to understand the kind of, or to characterize the dynamics of thermalization. And I want to look at particular cases where we do have extensive conserved quantities, such as the energy or particle number, the charge or the spin, etc. You name it. So we have like certain conserved quantities. And if we now prepare a state that has inhomogeneities, so for example, we have a system where there are more particles on the left than there are on the right, while the Hamiltonian itself is translation invariant, then as time goes by, the system wants to, as it approaches the equilibrium state, it would like to approach a homogeneous state. And for this, transport has to happen. So particles have to be transported from this region maybe to this region. In order to extract this directly from a microscopic Hamiltonian, it would be an extremely difficult task, right? So assume that we have a Hubbard type Hamiltonian. We want to understand how the charges equilibrate, how the transport is happening. We actually have to include an exponentially large phase space, and this will be extremely hard to solve. However, if we now look at different kind of time regimes, life can be easier. And this is now demonstrated in this timeline here. So this is now exactly for the type of experiment that I showed early on, where I'm now preparing a simple microscopic initial state, and I'm evolving this with respect to some Hamiltonian. So if I'm looking at the transport properties at short times, this will be non-universal and generically extremely hard to describe. However, at some intermediate times, basically before the system has reached its equilibrium, the system is believed to be governed by emergent hydrodynamics. So basically, the idea is that we have, after certain short times, we have a thermalization of intermediate size of cells, and then we can apply a universal description describing the transport at low frequency or in the long wavelength limit. And in fact, if we have systems with, for example, charge conservation, we can then ask how, for example, a charge that we place somewhere in the center of the chain is then spreading throughout the system. And this is then described by a diffusion equation. And in particular, from this diffusion equation, we can then predict that a wave package that we prepared will spread as proportional to the square root of time. So this is what we would call the diffusive dynamics. Good. So this was the case where we have thermalization, right? So basically where both the equilibrium state and also the intermediate timescales are then described by relatively few universal numbers. Now I want to consider a different scenario. I want to consider a scenario where, again, we are preparing a state of this type, but now we are adding to it a disordered potential, as shown here. For example, in the spin system, we could have a disordered, for example, z-directed field. And in this case, what can happen is that if the order is sufficient, if the disorder is sufficiently strong, then the system might undergo a phase transition into a different kind of dynamical phase, where the system, even after infinitely long times, does not reach this thermal equilibrium state. So basically, just by tuning the amount of disorder, the system is now believed to undergo a transition from a phase where the system, after long times, can be described by thermodynamics, to another phase where, even after infinitely long times, the system cannot be described by thermodynamics. So, and to summarize what I told you so far, like the overview that I gave so far, is that we can have, we can think of dynamical phases of matter where the tuning parameter could, for example, be the disorder strength, such that at low disorder, the system thermalizes and at long times is described by a few variables, such as the energy, temperature, or particle density. And then the system can undergo a phase transition into a phase where the thermalization breaks down. And this is, for example, the many-body localized phase. And well, what I have been talking about so far was mostly about thought experiments and some rather general ideas. But in cold atom experiments, this transition has actually been observed. So here is some experiment exactly in the spirit of the thought experiment that I just discussed. So we prepare here, or we not, but they prepare a charge density wave state. So where we have occupied and empty sites alternatingly, and measure the imbalance, right? So the imbalance, the charge imbalance between charges on even and on odd sides. So the initial state has a maximum valence, right? So because only the even sublattice, say, is occupied, and then this state is evolved in time. And what's then found is that in the case of small disorder, that this initial information that was encoded in the state, namely the imbalance, completely washes out. And this is what we would expect for a state that thermalizes. Once, however, the disorder is tuned above a certain threshold, it turns out that this imprint of imbalance never washes out, even to the longest times that are reached in these experiments. So this is a quite nice demonstration of this scenario kicking in, where we have now a dynamical phase transition between those two different phases. Good. So far, I talked now about two different, if you wish, kind of dynamical phases. So on the one hand, we have phases which thermalize, or alternatively, these are phases that are kind of fully ergodic, where we have a few conserved quantities and observables, such as the imbalance, for example, relax to their thermal values. And if we just look at the eigenstates of such system, then all eigenstates look thermal. So on the other hand, I showed many body localized systems where we have an extensive number of local integrals of motion. We have eigenstates that are non-thermal, and the system has a memory of the initial state, right? As I showed for the imbalance that didn't wash out. However, and this is what I also going to talk about in my talk in a moment, is that there can also be some intermediate behavior. And there are systems with constrained dynamics, and these are systems where it can happen that depending on the initial state, what you see might look like a system that is fully ergodic, or it might look localized. And these systems include, for example, gauge theories and quantum many-body scars. Right? So, and both of which have been observed in cold atom experiments. Good. So this was my short overview about thermalization and breakdown thereof. Maybe this is a time to take a few questions if there are any.
Okay, there's one in the chat. Do you want to ask it directly, Sam?
Or,
can we definitely say these are different dynamical phases and not a crossover? And can we also say that this is definitely only a dynamically different phase, so there's no phase transition in, for example, the ground state?
okay, I think I acoustically understood it. So first, regarding the second part about if this is only a dynamical transition, I would say yes, because if, for example, you take a model, if you take, for example, a one-dimensional spin chain model with, like if you take exactly this model that people usually look at, it's a Heisenberg chain with a disordered z-directed field. This is a model that in principle doesn't have any symmetries. And if you are in one dimension without symmetries, there's only one ground state phase, right? So in this model, you can construct, like for typical many-body localized Hamiltonians, there is actually no symmetry, and thus there's only one phase for the ground state. So if there is a transition of this type, this is independent of any ground state transition. Regarding the first part of your question, if this is a crossover or an actual transition, based on what we believe, or based on what we know so far, it appears to be an actual transition. So basically, if we are, again, think of this as a thought experiment, if we are at this very point, and if we just a little bit left of it, the system thermalizes. So meaning that the density matrix is actually of a thermal density matrix. We would have, if you look at entanglement properties, we would have a volume law, etc. If you look on the other side, for example, it has completely different properties, right? So the system, the reduced density matrix would not be thermal. In principle, we have area law states. So there has to be something happening. What type of transition it is not fully agreed upon. So there is numerical indication for this being costless-Thouless transition, which would also be compatible with RG arguments. But I would say that there's no, I think that the last word hasn't been spoken on what kind of transition it is. But I think taking in what's currently known about this, it appears to be an actual transition and not a crossover.
Thank you.
Great. So are there any other questions? This would be the opportunity.
Yeah, let me ask one.
So there's one from Piers. Do you just want to speak?
Can you hear me, Frank? Yeah.
Yes.
Okay. Now you can hear me. Just to stir things up, is many-body localization relevant at least to some approximation to solid-state systems, where of course there are things like high dimensions and phonons, or is it an idea that's restricted to low-dimensional optical lattices?
Okay, this is a good question. So let me just first give one answer in terms of trying to be mathematically rigorous. So there are arguments which not everyone buys, but there are arguments stating that many-body localization, in the sense that we are thinking about it, is only robust in one-dimensional systems. So what I mean is that if I basically play exactly this kind of game that I was just proposing, if you kind of make the distinction that whether or not after like evolving a system for an infinitely long time, you would get a thermal state, or you just get a state that's not thermal, there are arguments for saying that if you just do this for infinitely long, that for dimensions larger than one, that you will always get a thermal state. The timescales for this, however, are exponentially long in the system size. So I don't know how practically relevant this is. So far about mathematical rigor. There are, however, ideas discussed to applying these ideas to condensed matter systems, at least on certain timescales. So there are some hole burning experiments done at I think at ETH, which are, it's still controversial, but they are also discussed in the context of many-body localization. There are some dirty superconductors where this is discussed, but I'm not aware of any smoking gun experiment that everyone agrees upon.
So we can imagine, in principle at least, that over some time scale, we might be able to discover NBL states in higher dimensions in solid-state systems.
Right. I mean, what I think can happen would be like if you just look at, for example, at this cold atom experiment. This is also over a finite time scale. So this is over time scales of the order of 30 tunneling times. Who knows what's like, if we talk about mathematical rigor, we are asking what's happening after infinite time scales. So this is also not reached in these cold atomic systems. And if I, like for many systems, we can argue that there would be very long thermalization times, and that I believe can be realized in condensed matter systems.
Well, maybe I can ask these things later, but for example, could one imagine a fermionic system which loses its fermionic component of external conductivity, but of course the phonons will equilibrate it over some much longer time scale? Could one imagine that sort of thing happening?
Right, we would like to have, I mean, of course, if we want to isolate the system from its environment as strong as possible, and then we just need to get a regime where we see signatures of many-body localization in the time scale before the system would actually thermalize with its environment.
Thank you.
Okay, so I can't see any other questions for now, so I think we should probably move on, and then there's plenty of time to ask questions later on.
Good. Yeah, I mean, in this context, lots of work has been done, and I want to discuss two specific ideas. So the first work that I want to discuss is about entanglement growth in ergodic systems with conserved quantities. So, and I think that this is relevant because the way how entanglement grows tells us quite a bit about the properties of a system. And as a theorist, we usually calculate for Neumann entropies. However, what can be measured so far in cold atom experiments are so-called Renyi entropies. And one thing that I want to show is that in such systems, the von Neumann entropy and Renyi entropies actually behave qualitatively different. So this is the first part I want to discuss about. And the second part is about systems where we have charge conservation together with dipole conservation. And I want to show that the interplay of those two symmetries can actually lead to some interesting behavior and also a change from ergodic to non-ergodic behavior. Good. So let me start with the first part. So as already advertised, we get different types of different measurements of entanglement, and the probably most popular is the von Neumann entropy, which has lots of very nice properties, just given as the von Neumann entropy of the reduced density matrix. The generalization of the von Neumann entropy are Renyi entropies, which we basically can obtain from tracing the reduced density matrix to some power of alpha. And in this special case, when alpha goes to 1, we recover the von Neumann entropy. And this is what is quite exciting, is that if alpha is equals to 2, we can, in fact, well, there are several protocols that allow to experimentally measure the von Neumann, the Renyi entropy. And the key idea is that we take 2 copies of the system and we just can swap degrees of freedom. And then there are protocols performing this in cold atom systems, for example, using randomized measurements. And here in this plot, we see a result from the group of Innsbruck, where they actually study the dynamics, they actually measure the Renyi entropy for their system of an ion trap system at different times. So these are now the two quantities that we're interested in. And in fact, for understanding the dynamics of systems, by studying, for example, thermalization dynamics, it is quite interesting to look at the time-dependent behavior of the entropy of the entanglement in the system. And the question then is, how does the entanglement entropy grow? Right. So, and again, going back to the experiment or thought experiment that we discussed before. So we just now prepare a state that initially doesn't have any entanglement. So this is just a simple product state. And what we are now doing is we are performing a bipartition of the system into 2 parts, like in the left part and the right part. And at time 0, the entanglement is 0. So there's no entanglement between the left half and the right half. And now there's a very nice quasi-particle picture going back to Calabrese and Cardi to explain or that predicts the entanglement growth in integrable systems. So, and the idea is the following. At the beginning, we have now a system which consists of sort of localized quasi-particle excitations in the system. And as time goes by, these quasi-particles kind of expand or can within the light cone that I show here in yellow for one specific quasi-particle. So in the time before the first light cone hits this boundary, the quasi-particle is always on the left-hand side. So this quasi-particle, prior the time that the light cone hits this cut, is completely, if you just measure it, it's always in the left part. But the moment the light cone crosses the boundary between the left part and the right part, there's some uncertainty when measuring where the particle is. So this is now generating entanglement between the left part and the right part. And if we now have the simple picture of lots of independent particles evolving from this state, which is not an eigenstate, where we have a finite density of these quasi-particles, we see that the number of light cones that cross the boundary between the left part and the right part is increasing linearly, and thus the entanglement entropy grows linearly as function of time. So for systems that are described by quasi-particles, we have now a prediction that the entanglement entropy grows linearly. And it turns out, and there's some numerical evidence, that this linear growth also holds for systems without quasi-particles. And let me, in this context, discuss now a nice tool, which I also want to use. Yeah? Is there a question?
No, it's just some technical issues with computers connecting and disconnecting from Edo Rome.
Okay. Yeah. Good. So
sorry.
Yeah, sure. Go ahead.
Sorry, I should have raised my hand or something.
Go ahead, Katie.
So are you going to tell us more about the Renyi in a minute after you discuss the von Neumann, what the expectations are for the Renyi entropies?
Yes, so this is what I'm coming to in a moment. Yes. Exactly.
Okay.
Right. Thanks. Good. So now we have this kind of quasi-particle picture for the von Neumann entropy. And in fact, in this kind of quasi-particle picture, there would not be a difference for Renyi entropies. But let me now come, and this I want to also just take a little bit of time to introduce this as a quite powerful tool to understand the dynamics of quantum many-body systems out of equilibrium. And this is by actually not using a specific Hamiltonian for studying the dynamics of, for example, the entanglement, but just to look at a toy model that makes life much easier in many ways. And this is going back to some, I think that Adam wrote some of the kind of pioneering papers on this topic. And this is to use random unitaries to perform time evolution, or to perform an evolution of quantum states. And let me just motivate what I'm doing here in the following. So what I'm interested in is now this picture. We say that we start from a simple product state, and now we evolve it with some Hamiltonian. If we have some local Hamiltonian, such as the Hubbard model, etc., a way that we can think of the time evolution would be by using a Trotter decomposition of the Hamiltonian, and then we could draw exactly this picture that I'm showing here. Right? So we would have a picture where we start from a state, and now successively we are applying Trotter gates, and each of these Trotter gates would be just the exponential, or like e to the minus I delta t times the bond Hamiltonian. Right? So if we were to use these gates and a sufficiently small delta t, what this picture illustrate would actually be the time evolution with a specific Hamiltonian. This, however, is hard to calculate and also hard to understand. So the idea of these unitaries is now the following. We just replace the gates here by just random unitaries. So we just choose unitaries from a uniform distribution, and we just apply them. So now we have a system that's fairly artificial, I would say, because it has no locally conserved quantities, right? So it doesn't have any conserved energy, no conserved particle number, etc. So the only constraint is locality, right? Because these are local unitaries, so they are just having a light cone, right? So basically, if I'm doing this time evolution with the unitaries as shown here, and I'm just at a certain time, let's say that we are at this time here, then I see that only degrees of freedom that are covered by this light cone can be entangled, while degrees of freedom that are further apart than the light cone at this moment are completely disentangled. So they're still in a product state, right? So the only constraints that we have are locality and unitarity. But the hope is that from the solutions that we get, that we can actually tell something about the system. And the neat property of those random unitary networks is that there are many things that we can even calculate exactly. And one thing that we can, for example, obtain is the annealed average of the Renyi entropy. So as shown here, so what we can get is now the annealed average. So it's not the average, but it's the average of the exponential of the Renyi entropy. And this is given as a 2q, and q is the local Hilbert space dimension over 1 plus q squared to the power of t. And if we take the logarithm of this, and this is what we need to do for to get s back, this is growing linearly. So we find for a local unitary network, for these random unitaries, we actually get a linear growth of the Renyi entropy. And this has been taken further, including also early works by Adam, to look at different ways of applying random unitaries. So while I just presented here this brick wall unitary network based on or motivated by trotterization, one can also add more randomness to applying also in random locations, etc. And for all of them, it has been shown that both the von Neumann entropy and the entanglement entropy grow linearly, plus some corrections, but that I don't want to go into at this moment. Good. So, but now the question, this is, I want to look now not at systems without conserved quantities, but I want to look at systems where we have conserved quantities. And particularly the systems I want to look at are systems that have a U1 symmetry. So for example, we have SZ conservation as shown here. So in this case, we are again assuming this brick wall structure, and now we are choosing random unitaries which are block diagonal, right? So we have now a block of size 1 and a block of size 1 for both spins being up or both spins being down, and we have a block of size 2 where we have one spin up and the other spin down. So the caveat is that for these unitary networks where we have conserved quantities, stuff is no longer exactly solvable. However, it still yields significant simplifications. And I don't want to go to this in detail, but what actually happens is that we can write down an expression for the Renyi entropy, and for calculating the Renyi entropy, we have to calculate some average over basically 4 copies that we create, and calculating this average can be done by calculating a classical partition function, and this classical partition function has a strongly reduced degrees of freedom compared to the full quantum problem. So in this case, the use of these random unitaries doesn't provide an exact solution. However, it is then numerically much more doable than the full quantum problem. Good. So let us now have a look at the numerical simulations. So now we just take this network and we start from a simple Néel state and evolve it in time. And this is now what we find for the Renyi entropy. So here is on a log-log plot shown the Renyi entropy as 2, and here we plot the time. And what we see is for short times, it indeed shows something that is close to a linear growth. However, at sufficiently long times, there's a crossover to growth that goes as the square root of t. And this becomes even more clear if we look at the derivative. right? So here we have now done some experiment using the random unitaries, and we find that instead of having a ballistic growth, we find a diffusive growth of the Renyi entropy too. And again, from previous arguments, including from Adam, we know that the von Neumann entropy would grow ballistically.
Frank, we just have a question from Caden in the chat. Caden, do you want to unmute and ask that yourself?
Sure. I was just curious if we looked at these random circuit unitary evolutions, if we were to look at a subsystem, right? So look at some region, and I looked at the unitary, well, it wouldn't be unitary, but if I looked at the evolution operator on that subsystem, would that evolution operator, is it governed by some standard random matrix ensemble in the long time limit, or do we know?
You want to look at the operator acting only at a subsystem.
Yeah, exactly. So there will be some dynamical evolution operator for the subsystem. It won't be unitary because it's coupled to the boundary, but I could look at the long time limit of that. And so I'm just wondering, is that drawn from one of these, GOE, one of the standard Gaussian ensembles, or even if not the evolution operator, just what about the density matrix? If I were to look at the density matrix of a subsystem in the long time limit, does it look like it's drawn from one of the standard RMT ensembles?
Yeah, I would say so, right? So because this is a fully mixed state. But in fact, if
are you saying the density matrix is just
like if you just basically do this for infinite, like for
if I really go to all times, then I guess it's just the identity operator in the infinite time limit. I see. Oh, interesting. Okay. Okay, let's go on.
Yeah, just to briefly repeat what I wanted to say, like the key point, so that using these random unitaries without any conserved quantities, we have the great advantage that we just keep certain features of the time evolution, which is the locality and unitarity, and we can get lots of exact results when we just include conserved quantities, such as particle number conservation. It no longer is exactly solvable. However, it provides a method that is numerically much more efficient than studying the full system. We can actually go to systems where we don't have any finite size nor finite truncation errors, etc. So in fact, historically, this is what we first saw, and then we were quite curious because we didn't expect that. So then we just try to find, then we just look at a Hamiltonian system, and we look at our Hamiltonian system where the only conserved quantity is the energy, right? So this is a model where we have the Ising model with longitudinal and transverse field. So and what we find again is that, well, not as clear as before, but when we look at the Renyi entropies, that we see that there's a crossover at certain times, right? So the problem here is that the system sizes are smaller, so we just do see also finite size effect at long times, but still I find it relatively convincing that there is a crossover, because we see that the finite size effects are relatively small in this case. So the question is, like, how can we understand this, or why do we see actually this different behavior? And the idea is that rare events make the difference. So let us now have the following picture. So let us now think of a system where the initial state is just an X polarized state, right? So it's just the state where we have something like this. We have 1 over square root of 2 up times down. So this would be an equal-weighted superposition of all possible states in the z direction. So this will also include terms like this. It will include some contributions where there is a region of Z polarized state included. Right? So that's a superposition of many of exponentially many states, but some of them actually do have extended regimes where everything is completely frozen. And since everything in this regime is frozen, the entanglement can only build up fairly slowly, because the entanglement can only build up in a regime in which the domain wall is gone, right? In the system where we have diffusive transport, as I showed before, right? So if we have a conserved quantity, then the transport is happening with a diffusive behavior. So we would find that the melting of this domain wall, because of this diffusive transport, can only happen at a time scale of square root of t. Thus, the degrees of freedom that can get entangled would also only be of the order of square root of t. So, and this is now exactly what's happening. If we look at the spectrum of the reduced density matrix as function of time, we see that there are certain states that relax very slowly. And this is due to the fact that we have these rare states which relax slowly. And this now makes the difference between the von Neumann entropy, or more generally Renyi entropies with an index smaller than 1, and Renyi entropies with an index larger than 1. Right? So take in the extreme case the Renyi index to infinity. If it's infinity, then we would only take the logarithm of the dominant eigenvalue, and that is exactly what these kind of are exactly the extreme events that lead then to a slow decay. And this we can actually check further by taking a system of a bit more complicated random unitaries, where we have now a system which is like a Hubbard model, where we, however, do not allow double occupancy. Right? So it's just a Hubbard model where we just don't allow for any double-ons. So in this case, we have one block of size 1, which is when the sites are empty. And then we have states where a particle can hop like a particle of either spin can hop to a neighboring site. And we have terms where the spin is exchanged. So for this Hamiltonian, we can now choose different initial states. So for example, we can choose an initial state where we have an equated superposition of everything, right? So we have empty, up, down, and then this is a product state of all of them. And we see indeed this behavior that the von Neumann entropy, that the Renyi entropy shows diffusive behavior. If, however, we are choosing an initial state that does not have any zero contribution, so this does not contain any contribution of frozen states, we actually see a ballistic growth of the Renyi entropy. Good. So this actually concludes this part, where I wanted to show that it makes a difference what kind of Renyi entropy we calculate or measure, and in fact that predictions that are often made for the von Neumann entropy might not necessarily hold for Renyi entropies with an index larger than 1. Good.
Okay, I guess it'd be a good time to take questions if there are any questions in the audience. Okay, that seems not to be the case. So let's move on to the ergodicity breaking and dipole conserving Hamiltonians.
Okay. Good. In the second part, yeah, I want to look at.
Oh, now there's a question. Caden was too slow to type. You could just speak, Caden. Do you want to ask a question?
So is this idea that there's a difference between Renyi and von Neumann in the dynamics? Is there any similar distinction for equilibrium systems, ground states, or thermal systems?
This is a good point. So, I mean, I know in many cases where it's the same. For example, for topological entanglement entropy, I think generically it doesn't matter what kind of entropy you use.
And also, I think area laws, they both have area laws, but in the
Oh, no, but
gap
there is an interesting distinction for states. So if, for example, like there are certain states, maybe this is completely obvious, but if you take a state, for example, which would be just an equal-weighted superposition of random states, like if you just write down a wave function, which is a superposition of states with random positive amplitudes. That state is actually a volume law state for entropies, Renyi entropies with an index smaller than 1, and it's an area law state for, or it's a log growth, but it's certainly not a volume law state for Renyi entropies with an index larger than 1. So this would be another example where this is again due to similar effects, I think. And another important distinction is also like, for representability of MPS, right? So in order for a state to be MPS representable, we need an area law for Renyi index smaller than 1. So in principle, we can construct a state that has an area law for Neumann entropy, but yet it cannot be efficiently represented in terms of an MPS. So there are various cases where one has to be quite careful, I think. Thank you. Okay, so let me now talk about the second part where while in this part I only discussed one symmetry, right, where we have like one extensive symmetry such as charge conservation or energy. Now I want to take systems where we conserve the charge and the associated dipole of that specific charge. So let us now consider, for example, spin systems where the total magnetization is conserved and the dipole is also conserved. And there's something interesting if we conserve those two charges, if we just have these two conserved quantities, namely we find that excitations have very strong constraints on their mobility. And there's these are so-called fractons that also Claudio Chamon talking about. So, and there's a very simple way to see it. So let us now start from a simple state where we're considering a spin 1 chain. So on each side we can have either a spin 0, a spin -1, or a spin +1. And if we now start from a chain where everything is in a spin 0 state and we just act on it with an S+ operator to create one +1 state. So now this state by itself cannot move. It's completely immobile, because if basically this particle would hop to a neighboring site, it would change the dipole. So we start, this is a state where the dipole is 0. If the charge would hop over here, then this would be a dipole of 1. So the conservation of charge and dipole does not allow a single charge to move at all. The only way for a charge to move in the sector where we have Q equals to 1 is to emit a dipole. So the dipole itself can now move freely in this direction, because if you just move a dipole, we always have like +1, -1 as we move it 1, which means that the dipoles can move freely and the charges would be completely stuck. So we see that this dynamics has some interesting kind of constraints that we have to, that potentially have very interesting consequences on the dynamics. And there was a work showing that certain random local unitary dynamics with such symmetries actually failed to thermalize. And in this argument, they argued that this is quite generically the case. But the question that we wanted to address is like, how robust is this phenomenon actually? So, and for this, we did the following. We just write down simple Hamiltonians and study the dynamics of these simple Hamiltonians and look what's happening. And this is how we got into this. So we write down a Hamiltonian of this type, which is S plus, S minus squared, S plus, and this amounts to this kind of squeezing operation, right? So we just, if we just start with a state where we have 0, 0, 1, 0, then we would go from this state to 1, minus 1, 0. And these terms are designed in such a way that they both conserve the charge and the dipole. And now we just look at this Hamiltonian and perform, and we look at the dynamics of, or we look at the autocorrelation times at infinite temperatures. And what we see is that indeed the autocorrelations don't decay to 0, but instead to a finite value. If the system would thermalize to into an infinite temperature state, then this would not be the case, and instead it would go to 0, because this would be the infinite temperature expectation value. Now, this is what we call H3. So this is just basically, we have the system where we just act on 3 neighboring sites, and we just squeeze basically the charges into the middle. Now we just extend the Hamiltonian. So now we just take a system where we take H3 plus H4, and H4 is the same type of Hamiltonian, except that we just have a support of 4 sites as shown here. If we add this Hamiltonian, we see that the behavior is qualitatively differently, and what we see is now indeed after long times it approaches the thermal value. So this would be compatible with the system that thermalizes actually. Then we just take those 2 Hamiltonians and look at the eigenstates. And the eigenstates again look very differently. So when we take the eigenstates of this Hamiltonian with this squeezing, so which we call H3, the squeezing of 3 sites, we see that none of these eigenstates is thermal. In particular, what we plot here is the entanglement, the half-chain entanglement entropy as function of the energy density. And we see that none of those states, none of these eigenstates has reaches the infinite temperature or the expectation for an infinite temperature entanglement state, which is this dashed line, this is the page limit. If however we are looking at the spectrum of H3 plus H4, we see that there are many states that are not thermal, like many states that don't, like we have many states in the middle of a spectrum that have a very small entanglement, but the majority of the states looks like an ergodic system. So we see that states at infinite temperature, like states in the middle of a spectrum, approach the infinite temperature limit, like the page limit, as expected for a thermalizing system. So the question is now, what's going on and what's making these kind of 2 cases so differently? So we just now looked basically at the kind of emergent conserved quantities. So first of all, we find that the breakdown of thermalization is due to many conserved quantities, or extensive number of conserved quantities that arise in this limit. First of all, we have exponentially many frozen states, like states that have no dynamics at all. In particular, using a local rule, we can actually construct exponentially many frozen states, and using a sort of simple kind of Pollmann estimate that was originally used for predicting the degeneracy of water ice, we find that there's some exponential number of states that serves here as a bound in this case, compared to the exact degeneracy. So despite technicalities, I mean, we find that this Hamiltonian has an exponential number of eigenstates that are simple product states. Right? So these are completely frozen states. And then we have also other conserved quantities. So for example, if we start from a state of this type here, then we find that the sign of the right and leftmost charge in any region of space is conserved. So we see that using this conserved quantity, that the system, like the eigenstates and also like the states dynamically, decay into certain blocks. So if we just, for example, look at the picture here, we start from a specific initial state, and then we see that there's dynamics only in this block, which is completely decoupled from another block. And let me now come to what's probably the most important observation, is that now we just observe that the Hamiltonian has a block structure, so where we have many different disconnected blocks. And one question is, like, if we look at the largest block, right? So then stepping back, so if we just take a system with a U1 where we only have a particle number conservation, we of course have also a block diagonal Hamiltonian. However, if we look at the largest block asymptotically grows exponentially with a local Hilbert space dimension to the power of n. So this is why the system eventually is ergodic and shows this thermalizing behavior. So now the question is, like, if we just look at this block structure, or this emergent block structure that we get due to these kinetic constraints. And what we find is that the largest block in the system is actually can be described by spin 1/2 degrees of freedom. In particular, the largest block are those configurations where subsequent charges have opposite signs. This is like some sort of string order, if you wish. And this can be just described by spin 1/2 on the bond. Right? So we can just represent all these configurations by just simply saying that we have the same spin, and whenever we change from a down spin to up spin, then we just place a plus charge, and when we change back from up spin to down spin, we just place a minus charge. And so this is basically the derivative of the magnetization. So there's a one-to-one mapping of all those configurations to spin 1/2 degrees of freedom. And thus, we find that the largest connected sector has a dimension that scales only exponentially with 2 to the power of n. So the largest connected sector is actually of vanishing size compared to the overall dimension of the Hilbert space. And this is something that we call now strong fragmentation. So due to these local constraints, we find that the system can only explore a very tiny fraction of the Hilbert space. Now, what's different for H3 plus H4? So one thing is actually the same. We also have an exponentially number of frozen states. And again, we can just come up with a procedure to construct frozen states, right? So we have again a construction that allows us to find exponentially many frozen states. However, and this is now the important difference, if we look at the largest connected block, we find numerically that the largest connected block actually contains basically all configurations. So what we are plotting here is now the maximum, like the dimension of the largest block divided by the total dimension of the block described by the global quantum numbers of Q and P. And we see that while for H3 alone, this goes down exponentially as 2 to the n divided by 3 to the n, while for H3 plus H4, this remains of order 1. So this is constant. And in this case, we still have exponentially many sectors that emerge due to these local constraints. However, the largest connected block is still containing almost all configurations. And this is what we call weak fragmentation. So we have now, and this is now summarizing basically the findings, so that we have Hamiltonians that conserve both Q and P. If we just take the Hamiltonian H3, we just say it's strongly fragmented. So we have like an exponential number of sectors, and the largest block grows slower than the than the Hilbert space. And if we take H3 plus H4, we would say it's like weakly fragmented. So we have an exponential number of different sectors. However, the size of the largest block is having the same size as the Hilbert space. Good. These are the main point. Let me now add a few bits to it. So there was a work by Morningstar, Kimani, and Hughes who explored exactly these type of Hamiltonians, while we were looking at infinite temperature states, so where we just basically look at half filling, which is the largest sector. So we look at the Q equals to 0 sector. They actually looked at the fragmentation for the Hamiltonian H3 plus H4 as function of the charge density, right? So basically the charge density, if the charge density is 0, all spins are down. And if the charge density would be 2, it means that all spins are up. And this is everything in between. And what they found is that the dynamics exhibits actually a transition. So at low densities, the system is strongly fragmented, and at large densities, it will be weakly fragmented. So there's actually a transition as function of the filling density. This is one bit I want to say. And then I mentioned early on in the beginning that in systems that thermalize, that the system at intermediate times can be described by hydrodynamics, right? In particular, we discussed that when we have systems where we only have charge conservation, that we can use Fick's law and then get diffusive transport. So basically, we found that if you just create a charge excitation, like you just create a charge, you put some charge into your system, and you just ask how it then distributes over the system, that goes as a square root of t. Now we just can play the same game, so we can again derive hydrodynamics for systems that thermalize, for example, H3 plus H4, and has both Q and P conservation. And what we find is that they get a different hydrodynamics, where instead of diffusion, we find that the spreading goes as T to the power of 1/4. And more generally, we could derive that if we conserve the mth moment, right? So for dipole, m is equals to 1, we actually find, or this hydrodynamic description predicts that the autocorrelation functions, or this peak here, would go down as minus 2 to the as t to the power of minus 1/2 times m plus 1. This we get from the hydrodynamic description, just building in the extra conserved quantities. And now we can compare to numerics, which we did on the one hand comparing to cellular automata, where we looked at conservation of dipoles and quadrupoles, and we find that the prediction from hydrodynamics is actually in quite good agreement with the numerics. And we also looked at the Hamiltonian system, exactly the same one. It's the same type that we looked at before. And again, we find that at least for larger system sizes, that the predictions of 1/4 are in quite good agreement with the numerics, albeit there are pretty strong finite size effects. Good. In the remaining few minutes, let me just briefly sketch over or discuss some ideas how we can realize this physics in cold atom systems. And the starting point is now a system where in the non-interacting limit, we would have Stark localization. So basically what we do is we just take now a system. In particular, we could take a system where we have fermions that, or bosons, whatever. We have now particles that can hop between neighboring sites, and we add to it a linear potential. Right? So this is exactly the picture we have drawn here, and we add to it. Right? So if we just take only this part, we know the answer. The system would just we would get Bloch oscillation. So we have Stark localization. If, however, we are adding to it some interactions, we can now perturbatively generate terms that would couple basically the degenerate states in the limit of large delta. And in the limit where the tilt is very large compared to the coupling, basically if the tilt is very large compared to the coupling and to the interaction, in this case, the type of terms that will govern the short time or intermediate time dynamics are exactly of the type we were just discussing, because they would be dipole conserving, right? Because if a charge would just hop to one side just by itself, it would just it would increase the energy, and this is not going to happen because of energy conservation. So perturbatively, what we would get in this case to lowest order would be terms where this one particle hops up, the other particle hops down. So these would, to lowest order, be the contributions that would yield dynamics in these otherwise stark localized systems. However, as we tune now the U, like if you just now assume that we're in a regime where the hopping J is small compared to delta, if you now tune U, then we can get also into different regimes. In particular, if U is of the order of 2 delta, then then we can have certain resonances, right? So basically particles can hop, actually now a single particle can hop down and create then a double excitation, right? So we have certain resonances, and this we can now first numerically calculate, because we can now look at, for example, the return probabilities as we tune the parameter delta and U, and we see nicely that there are these lines where the return probability is reduced, and this is exactly where we have these resonances. Good. And now we can compare these pictures to experiments, and well, there's lots to say about these experiments, but given the time constraints, let me just focus on a few important points. The first is that by comparing the theory and experiments, we find that there's an excellent agreement of the short time dynamics in the limits where we can still simulate it and the actual experiments. And what we also see is, as we tune this parameter U, that we see the resonances that I just talked about, right? So if we just measure again the imbalance, as we did very early on when we were showing the results from many-body localization, we just see that there is a dip in the imbalance where we have these resonances. And the last slide I want to show is that where we now directly compare the effective Hamiltonian, like Hamiltonians of this dipole conserving type that we derived perturbatively, with the experiments over fairly long times, and we see that there's a pretty good agreement. So what we are comparing, we having the same type of Hamiltonian, but we are changing now the doublon density, and the Hamiltonian in different doublon sectors gives different results for the imbalance, and we see at least pretty good qualitative agreement between the numerics, which are these solid lines, and the experiments. Good. Yeah, let me conclude here with the summary. So and I'm happy to take questions then.
Excellent. So first, let's thank Frank for an excellent talk. So there was one short question in the chat. Maybe let me just extend it slightly. So it was Jared Retnam's question about whether the underlying spins were spin ones, and I think they were, but I mean, does it matter? Can we have different spins, and would they still display the same phenomenon if you took a higher spin to represent the same Hamiltonian?
Right, this actually has an effect. So we looked also at this. I'm not showing this in this plot, but if we just so we could now just plot the same picture for different Hamiltonians, so for different spins. And in fact, what we see is that if we take a spin 1/2 system, then if we take then we need to take H4 plus H5 to make it ergodic, and H4 itself would be not ergodic. So H4 would be strongly fragmented, and H4 plus H5 is then weakly fragmented. And if you go to S equals to 2, even H3 would not be strongly fragmented, but weakly fragmented. And then from there on, everything is then weakly fragmented. But let me add one more comment. So this kind of idea of weak and strong fragmentation is not limited to these dipole conserving terms. So if, for example, we look at these Hamiltonians that we derive here perturbatively, like even those at the resonances exhibit this kind of fragmentation that I discussed. So also none of those would be ergodic. So none of these would lead to thermalization. So only at higher orders this would happen.
Excellent. Good. So other questions from the audience?
So I know in the usual case of many-body localization, in Fermi-Hubbard chains, I think the SU2 symmetry plays a pretty important role. There's maybe some difference about localization with the charge and spin degrees of freedom, or at least some people were conjecturing this at some point. Is there a similar distinction in the case of the tilted localization or the kinetic constraints?
Right, to make the point that if we have SU2 symmetry, well, more generally, I mean, there's a statement that if we have non-abelian symmetries, that there cannot be many-body localization. Here, the issue is that I wouldn't know exactly how to do this one in a SU2 symmetric way, but because now, so now we have this field, so then we still have an SU2 symmetry for the spins. So the spin degrees of freedom, it's hard to make. So here, like the kind of localization that we look at is just basically looking at the localization of the charge degrees of freedom. So
so this delta up and this delta down, they have to be different?
No, this is right.
Okay.
So I didn't comment on this because this is just in the experiment there is a slight discrepancy between up and down, but this is actually tuned such that it's as low that we can really compare to numerics, which is
okay. Mm-hmm.
where this imbalance or like the difference between up and down is neglectable. And let me also stress that if we have systems with this linear potential, we would never expect, at least not theoretically expect from what we know, that there would be a localization for infinite times, right? So because all are making statements about the low order perturbation theory. So if we just basically would study the system at very, very long times, higher orders of perturbation theory would be relevant, and the system would, like following this simple-minded theory, would be always expected to thermalize. So in order for localizing the system, we always have to do some other perturbations, right? So for example, we would still have to add some amount of disorder, or we would have to add other deformations of this linear potential. But following these ideas, we would never expect this to be fully localized in this sense that it never melts after infinite order. Yeah.
Are there some good examples of higher dimensional realizations of similar problems? I mean, can you have dipole conserving quantities, say 2 components of dipole moment be conserved, and would that lead to similar physics or not?
Right. Actually, yeah, with one bachelor student, we are looking into this, that we just use these cellular automata that conserve quadrupoles on two-dimensional lattices, and there are indeed similar phenomena, and a few things are actually a bit different because you have then some subsystem symmetries that play also a role.
Thanks. So, some more questions? Okay. Then, I mean, maybe connecting to the question that kind of Claudia Schumann was hoping to touch on, I mean, as to whether or not there are some continuum limits of these systems. Right? So here we're talking about lattices. So can you think of some natural limit of some code outcome system where we don't have to use a lattice in order to generalize subsystems? I mean, we can ask in theory.
I mean, dipole conservation, like the dipole and charge conservation are well defined also in the continuum limit. So in this limit, this should not be an issue. As for the dynamics, I'm a bit puzzled. I mean, I don't know if we just go to the continuum limit, what kind of measures we would use. So I would have to think more about it. I mean, this is a very good question, but I can't really. I mean, the fact that we're not relying on sublattice or subsystem symmetry, we just really have charge and dipole conservation, both of which are perfectly defined in the thermodynamic limit. So I don't think there would be any conceptual issue. Just a question how to deal with this locality. Because if we just basically go to the continuum limit, then we just have lots of degrees of freedom. And that tends to make the system more ergodic. So I can't do this in my head now. So, but I think this is an interesting question. So how this limit would behave. But I don't know a firm answer. Oh no, actually one thing, not with respect to the weak and strong fragmentation. However, all those arguments that I gave before for the properties within the thermalizing phase, or like that happens in the phase in which we have weak fragmentation, this is indeed derived in the continuum limit, right? So these transport properties will not be affected.
Okay.
But again, I mean, for these weak and strong fragmentation, I would have to think what are proper definitions of those statements in the continuum limit, which I wouldn't know.
Actually, could you give us some more intuition as to why this is the hydrodynamic formulation of this generalized system? I mean, is it a straightforward generalization, or is there some further insight?
It's more or less straightforward. You just look at how Fick's law is affected by these extra conserved quantities, and then you just find which orders contribute, and then you just can derive these results.
So it's just expansion order by order and canceling terms. Great. Okay, so let's see if I missed any questions in the chat up there. Okay, yeah. So I mean, I guess the main distinction between the first topic and the second topic was that in these dipole conserved systems, we don't necessarily have any true phase transitions, right? I mean, so here is just a matter of the conservation laws changed the long-term dynamics, but you don't have a strict, you don't have any strict non-thermalization in the infinite time limit, I guess, right? Is that correct?
Well, no, it's not necessarily. I mean, like if we take this, I mean, it depends what kind of system you're talking about, right? So if we take a model where we actually just take, as shown here, so we have a model of the type of H3 plus H4, and we vary the density, there appears, according to the paper by Vedika and David, that there is a transition. So if we just go above a certain density, that the system is it basically becomes ergodic, and below it becomes strongly fragmented.
That's
so if you are in this regime, it would never thermalize even after infinite times, and while in this case it would for a typical state. That's a big. This is the question. So let's take a typical state, and you just evolve it with the Hamiltonian. And their statement is that if you just take a typical state with a density of something around 1, it would never thermalize. If you take a typical state with a density of the order of, I don't know, 1.7 or so, then it would thermalize. However, if we take these physical systems, like the ones that where the starting point is the Fermi-Hubbard model, then we would have to include all orders at infinite time. So in those systems would indeed never thermalize. There would not be a transition.
So in a different way of saying this would be that the effective Hamiltonian has to be strictly local, right? So any longer range terms would kind of melt this. Yeah.
That's right. Yeah.
Excellent. Good. Wow. Any other questions? If not, we are coming to the end of our allocated time, so we should probably just thank Frank again for an excellent talk. And well.
Yeah, thanks very much. Again, thanks for all the questions and discussion.
Yeah. Good. So condensed matter physics in the city will be back tomorrow at the usual time, 2 p.m. Actually, is that true? I think tomorrow we have 3 talks, so I think we might have some slight change in schedule. Let me actually just get that up. It's a longer day, so we might start half an hour early or something like that. Yes, so 1:30 is the time. And we also have some contributors